Okay, so for the last talk of this morning, I'll go slowly. The last talk of this morning, Brian Collier is going to tell us about something different from what was originally announced, but the title is there: Conformal Limits for Parabolic Higgs Bundle. Oh well, good question. Should we wait for Oscar? I don't know.
Oh, I already got all the jokes out of the way about.
Okay.
All right, good, thanks. Yeah, so it's a great pleasure to be here on the occasion of Oscar's 60 plus epsilon, I think, as we agreed, birthday. Maybe I've known Oscar a little less time than the other speakers, but still, I think it seems like the years are adding up now. I think it was in 2014 in Aarhus we maybe met. Yeah, and since then we've been, I don't know, I've been to Madrid some number of times that I've lost count of, and we've had some great discussions about math, and also other than Lie theory and is something we kind of share a common interest in. We also share a great interest in eating, I think, and we have bonded over a lot over Spanish and other cuisine. Okay, great. So let's get started. The talk title is called Conformal Limits for Parabolic Higgs Bundles. It's joint work with Laura Fredrickson and Richard Wentworth. It's not on the archive yet, but hopefully will be soon. And okay, I don't need to say that. I'm not talking about what I wrote my abstract about. Great. Okay, so X is going to be a compact Riemann surface, and I'm going to fix E rank n smooth vector bundle on X. Okay, and I usually think of it having some sort of trivial determinant and SLNC objects, but I probably won't be. I won't write that as we go along. Okay, so there are these two moduli spaces that I think we mostly all know and I think love. This one I'm going to call M0 for today is the Higgs moduli space. And then there's another one. And then there's another one, M1, which is the moduli space of holomorphic connections. And of course, there's a map which identifies these two that I'll call T1. Okay, so explicitly, what does it do? It takes a Higgs bundle, so a holomorphic structure on my bundle together with a holomorphic endomorphism twisted by K, and sends it to a holomorphic connection, which I'll sometimes remember to put this one here, which I'll write like this here. So this is a new holomorphic structure, and this is now a connection, and together that's a holomorphic connection because H solves the Hitchin equation. Okay, so good. This is maybe more generally, as we saw in Carlos's talk, there's a bigger moduli space, which I'll just consider the one over C, called the Hodge moduli space, of holomorphic lambda connections. Okay, and this is some space where this is the 0 fiber, this is the fiber over 1, and that's where the notation comes from. So a guy here is a lambda holomorphic structure in a nabla, where nabla of Fs is lambda Bf tensor S plus F nabla S, and it's holomorphic. Okay, and this map T1 actually foliates this space by sections. So there's a map T from C cross M0 to this space, which takes lambda and a Higgs bundle and sends it to, well, the lambda connection, which is that guy. Okay. Good. And so I said it, this foliates this space by sections. And I don't know, sometimes it's more convenient and I think more natural to think about lambda connections, but sometimes it's also useful, or things become more transparent if you think of these instead of lambda connections as a C star family of flat connections. Up. So I secretly mixed both. The lambda should go on the connection part so that it satisfies the lambda scaled Leibniz rule, but the family of flat connections is given by this. Okay, good. Okay, so that's the non-abelian Hodge correspondence. In the title, there's this other thing called the conformal limit. So what's the conformal limit? Conformal limit is another map which foliates this space by sections. So it's a map which I'll call CL from C cross M0 to M Hodge. Okay, and now let me define it for you. So let me do it in a few steps. So R is going to be a real number. It's going to be positive. So what I can do is I can apply, this non-abelian Hodge map to the Higgs bundle where I scale the Higgs field by R. And now the answer over here, the metric I use, depends on that scaling factor. So let me kind of get there in a bit. So I can consider the connection. I should leave a little space. R adjoint of the Higgs field with respect to the metric, which depends on R, plus the Chern connection of that metric, plus phi, R times phi. Okay, so that's something I consider. That's a way to get a one parameter family of holomorphic connections. But I can also do this thing here where I multiply the adjoint part by lambda and the Higgs field part by lambda inverse. So I can put a lambda here and a lambda inverse there. Okay, so now I have two parameters. And the conformal limit is something where I fix the ratio of lambda and R so that I now have one variable, and I'll take the limit as that variable goes to 0. So what I'm going to do, let me just make sure I get it right, is fix H bar to be lambda over R. And then I'm going to define what I'll call C. Let's see, I think I want my H bar down here, R of D bar E phi to be equal to the limit as R. Oh no, I'm going to run out of room. The limit as R goes to 0 of this guy. Okay, so lambda times R in terms of H bar is H bar R squared. Okay, so H bar R squared phi star HR plus DHRE plus H bar inverse. Okay, and what's the conformal limit? It's, well, this limit. So sorry, I messed it up. That's supposed to be C, and then the conformal limit is the limit as r goes to 0 of this family. Okay, so that's a flat connection, but now I'm going to multiply it by h bar to get an h bar connection. Does that make sense? So this is going to take h bar and a Higgs bundle and send it to h bar times. Oh, I messed up something. Sorry. I didn't really mess up anything, but I wanted to say what equivalence class here. Okay, so to now h bar inverse limit r goes to 0 of c r h bar d bar e t. Okay, so if this last bit was confusing and where I put the equivalence class of where I was taking the limit, don't worry about it because part of the theorem says I can put it in either place. Okay, so this is the conformal limit. I've defined it for you. Other
H-bar inverse.
so this is the way I've defined it is a flat connection or a one connection, and the way there's a C star action on this space, and the way I go from a one connection to a lambda connection is I multiply this term by lambda inverse. So this should have been an H bar. Okay, good. Great. Okay, so where does this is the definition, but where does it come from? It comes from physics. I can't tell you why, what the physics is around it. But I'd be happy to know if you could tell me. But so Giotto conjectured that this process of taking the conformal limit, if I applied it to a very special set of Higgs bundles in this space, namely the Hitchin section, I would get a very special type of holomorphic connections over here, one which is also parameterized by the vector space of holomorphic differentials, and that's the space of Opers. Okay, so maybe I should write that. Giotto conjectured conformal limit takes Hitchin section to Opers. And this was proven by, let me just write the letters first. Dumitrescu, Fredrickson, one of the people on this project, Kitanakis, Mazzeo, Mulesi, and Neinsky. Okay, and then kind of building on this work, Richard and I, proved basically that this conformal limit one exists almost always and identifies certain nice holomorphic Lagrangians in this space and this space. Okay, so let me first draw a picture of what I think of this is going on, and then I'll state the theorem with Richard. And then the point of this talk is to talk about what happens in the parabolic case. So here's my space M0. Here's my space M1. So if I have some point X, I can look at the C star orbit, which I'll just call Rx. And that, of course, converges to some point there. And I can do non-abelian Hodge. So I'm going to talk about the value at H bar equals 1. So here's T1 of X. Here's T1 of the whole family. And well, what this conformal limit construction does, sorry, let me just find the CR. this guy says, well, I apply non-abelian Hodge, and then I get some family here, which is CR1 of X, and I'm taking a limit as R goes to 0, and well, one, it's just when the limit exists, and at some point here, which I'm calling the conformal limit of X. Okay, so it's a different map. And if well, it turns out, as we'll see in the theorem I'll state, if I do this to the points along this family, I'll get, well, the picture will look something like this. So this will be the conformal limit of R times X. Okay, so this is a kind of cartoon of, I don't know, how the conformal limit and the non-abelian Hodge are, quite different.
Another naive question.
Yeah.
When you said limit is R goes to 0, am I just allowed to set R equals 0 in that expression?
No. Well, because it won't be flat, I imagine. Because I would say that Chern connection would be flat, I guess, if you said that. I guess one, you don't know what HR is, but if that was something that converged, I think this would just say this is holomorphic, and then you would get a flat unitary thing. I mean, that could be, I mean, I don't know, but that's not the answer. That is the answer we'll see in a special case when the underlying bundle is stable. Okay, so that's a special case of when this happens, but it's somehow at the opposite extreme of the Hitch section, which is what Gayota's conjecture is about. Okay, so what's the theorem? So this was maybe not so long ago, but it was, pre-pandemic, so it's a whole lifetime ago. The statement is, if the limit as R goes to 0 of dB on B is stable. Okay, so the limit always exists, but it could be strictly polystable. But if it's stable, then one, the H bar conformal limit of D bar E phi exists. Okay, good. This is about that map being well defined, right? If the limit didn't exist, then I shouldn't have told you about the previous part. Two, and this is so I define the conformal limit here as well. I look at this flat connection, I take its kind of equivalence class, you might think of it in moduli space, and then that gives me a family, a path in the moduli space, and I say it's the limit of that path, right? So that's something about this limit existing upstairs up to gauge. But in fact, the limit exists upstairs already, not just up to gauge. Okay, so all I wanted to say is limit R goes to 0 of this C R H bar T bar E B. Okay, and this will be a kind of, this is an important point because in the parabolic setting, I'll just say that. That's why I'm kind of stressing this. And the third thing is, well, it's not, we kind of don't just prove that it exists. We find good coordinates where we can compute what it is. So let me just say that the conformal limit can be computed explicitly in, I'm sorry, we call global slice coordinates around the associated Hodge bundle. Okay, so let me say what I mean by that. Okay, any questions? I should say. Yeah. Here? Yes.
Three of that.
Here.
The one that was
From H bar inverse to H bar.
Right, I guess I'm just going back and forth between thinking of it as just a flat connection, which depends on something called H bar, and then an H bar connection. So let me think of it as a flat connection and say the limit exists, and the way you get the associated H bar connection is you multiply by H bar. So this family here, which you're taking the limit of, is of flat connections. And in the end, I'll get some flat connection, and then I'll scale the 1,0 part by H bar to get the H bar connection. Does that make sense?
Yeah, but isn't there? Should be right H bar.
Didn't I? This H bar?
No, multiplying by.
Oh, you want me to put an H bar here? Okay, I was gonna say this is like of the flat connection, and then if you want to get the H bar connection, you multiply by H bar. Okay, sorry if this is causing extra confusion, which I'm going back and forth. Okay, so what do I mean by 3? So if the limit as r goes to 0 of e bar e phi r is, so the Hodge bundle, which I'll call d bar 0 phi 0, where well, maybe E0, which is d bar 0 is, well, the direct sum of k holomorphic bundles, and in this splitting phi is, you know, this has this form, then there exists a unique gauge so that my bundle I'm interested in computing the limit of, d bar e, is d bar 0 plus beta, and phi is phi 0 plus psi, where, well, beta is upper triangular. So beta is a 0-1 form valued in the endomorphism bundle of E, and it's with this decomposition, it's upper triangular. So is strictly upper triangular. Psi is just upper triangular. Okay, that's, I wouldn't get uniqueness if I said this, but they satisfy equation, which is a slice equation. So d0 beta plus phi 0 star psi is 0. Okay. And okay, so these are the slice coordinates for a Higgs bundle that flows down to this given fixed point. And in these coordinates, the conformal limit of d bar e phi is equal to, well, I basically apply non-abelian Hodge to the fixed point, and then I add the beta and the psi to the resulting holomorphic connection. So that means I look at d bar 0 plus phi 0 star plus beta. Oh, maybe this is what I'm understanding the confusion is. If I want to put an H bar, I need an H bar here. Plus the Chern connection of the metric at the fixed point plus H bar inverse phi 0 psi. Okay, so that's the answer to the conformal limit in these nice slice coordinates. Okay, so if you're in the Hitchin section, then, well, it turns out you can take, in these coordinates, beta is 0, and you're adding holomorphic things in the kernel of the adjoint of the Higgs field, and that's highest weight spaces of some SL2 representation. That's what these slice coordinates are. It's exactly how the Hitchin parameterization was, Hitchin section was parameterized. And what you're getting on the right-hand side is you apply non-abelian Hodge to that uniformizing Higgs bundle. Beta is 0, and I'll add holomorphic things in highest weight spaces, and that's how Bailenson and Drinfeld parameterized opers using the Hitchin base. Okay, so this is why they link up. I've lost track of time. How long am I supposed to go? Quarter past. Okay. Okay, good. So that's the somehow non-parabolic setting. Are there any questions? Okay, so I'll spoil where we're going. The theorem is that, well, you can make all of these statements the same as I just made them in the parabolic setting if you assume you're in the full flags setup. Okay, so full flags, and it's very important for the kind of analysis behind finding these slice coordinates that you're in the full flags case. Okay.
Of the flow to stage it to the conformal limit, or, I mean, rather than just that the limit, but the whole flow, like in this upward and downward flows.
The R family, or
Yeah, the whole, if you start with a Higgs bundle,
yeah,
you consider all the points that go and
to one point, right?
is there anything like meaningful for that?
Yes. So the things that all flow down to this given fixed point, which I called that guy, d bar 0 phi 0, are all of the lambda connections, such that when I act by C star on the Hodge moduli space, well, that limit exists due to a theorem of Simpson, and those are exactly the things which have this limit. Okay, so the conformal limit, I mean, I'm kind of talk so much about, I'm not going to talk at all about this, but what it does is in Tomasz's talk, we saw that the set of things which flow down is some holomorphic Lagrangian in the Higgs moduli space. The set of things that are, say, holomorphic connections under the C star action on the Hodge moduli space, which have limit this guy, is a holomorphic Lagrangian in M1, and the conformal limit identifies them. And that's true for every stable fixed point. Of course, they're holomorphic with respect to different holomorphic symplectic structures, so it's part of the interest. Okay, so what's the parabolic setting? So maybe I should just start with, well, I said something there, but in the strongly parabolic setting, all of this is somehow works exactly the same. But in the non-strongly parabolic case, when you allow yourself to have eigenvalues of the residue, some new phenomena happen. Basically, because when you apply non-abelian Hodge, your parabolic structure on your connection depends on the eigenvalues of your Higgs field. But as I look at this family, I'm scaling the Higgs field, and I'm okay. Anyways, the weights of the holomorph of of the holomorphic connection are changing in this family. So they're not really, it doesn't make sense to think of them as happening in some moduli space because the thing you fixed to define the moduli space is changing in the family. And so, okay, so that's, we'll see what's going on. Okay, so let's do it. So let's fix D, a divisor, an effective divisor. And what I'm going to do is, remember I fixed my smooth bundle at the beginning. So I'm going to fix a flag, EP in the fiber over each point, and the full flags case is when this is a full flag for all P. So NP is N, which is the rank of the bundle for all P in D. Okay, and then a little bit more of notation. Let's let P, so math frac PP, be the subalgebra of endomorphisms of the fiber preserving the flags. And of course, there's a sequence, which are the nilpotent part, which are the things which bump me down the grading, so they don't. And then there's the quotient, which is the Levy part of the parabolic. So those are the things which preserve those, say, graded pieces of the associated graded. Okay. So I'm going to just follow some what was kind of previous words for these things. So we'll call it, well, I'll just say we get a quasi-parabolic Higgs bundle. Is just going to be, well, a holomorphic structure on the bundle and a Higgs field, where phi is a holomorphic section of the endomorphism bundle of E twisted by KD. Okay, so I'm allowed to have simple poles at the divisor, and I'll insist that the residue of phi at P preserves the flag. So that means it's in this subalgebra. Okay, great. So let me just note, I have this res map where I project onto the levy. And maybe let me call this map pi P. Not right now, but I will. So I just wanted to define the full flags cases when I do that. And I will quickly do that, but yeah, okay. This goes from my parabolic Higgs to the products of the levies, which just takes and projects the residue of phi P onto the levy part. Okay, and then in this setup, what's called strongly parabolic is, well, the inverse image of 0 under this map. Okay, they're the ones where this projection is 0, meaning that it's in the nilpotent part. Good, and maybe I should just say it now, as Anna was suggesting, that in the full flags case, this levy part, okay, this res is just the eigenvalues of the residue of phi at the various different points. Okay, and then with the same, definition, you can, not same definition, but with the same, spirit, you can similarly define, I guess what should be called quasi parabolic lambda connections or logarithmic lambda connections. Where here, again, the residue of so nabla will go from E twisted by K D, and its residue you want to assume is in P. Okay, so those are just the objects. And to define moduli spaces of things and to do non-abelian Hodge, you need to choose weights on your flags. Okay, so to define moduli spaces, we choose weights. And with this data fixed, I can define the notion of an alpha degree and alpha stability and stuff like this. And there is a moduli space which I call P0 alpha, which was constructed by Yokogawa of alpha semi-stable parabolic Higgs bundles. Okay, and for alpha generic, alpha semi-stable, this implies alpha stable, and so this is a nice smooth object. And the point of doing things like this, where I don't, well, like say, fix the value of the residue, is I want a moduli space with a C star action on it. And this big space has a C star action, whose limits, as you go to 0, exist and are in the moduli space. So whenever you, other than the strongly parabolic case, whenever you fix some residue data, well, usually that's not preserved by C star, or it's preserved by C star, but maybe in the limit you you jump out of that condition. Okay, so that's why I want to consider this larger space. Okay, there's also a nice moduli space of lambda connections, which I'll just call P alpha, which fibers over C, constructed by David Alfaya. Great, and then the kind of key takeaway from what I want you to remember is that non-abelian Hodge does not define sections of P alpha. Okay, because the weights need to change if the eigenvalues of the residue are non-zero. Okay, but the conformal limit does. Okay, so now I'm going to assume I'm in the full flags case. So let's just now assume full flags. And I should say, like, one of the things we need to do carefully, which is not the way you construct, or Yokogawa or David Alfaya constructed these moduli spaces, is we need to construct them in a gauge theoretic way. if we want to say mimic what the things I had here, which really depended on understanding the moduli space as a gauge theoretic object. Okay, good. So let me see if I can do this in the time remaining. So in full flags case, which I just said, what is non-abelian Hodge? Well, it says that if I have a alpha stable bundle, a Higgs bundle, alpha stable, if and only if there exists a metric H, which is adapted to the weights alpha. Okay, since I'm assuming full flags, that's all I need. In general, it also depends on the Higgs field. It depends on the nilpotent part of the Levy projection of the residue, but that's 0 in the full flags case. Okay, so that I have a solution to this equation. So what does it mean to be the metric to be adapted? Well, Carlos told us. It means that, well, in a local holomorphic chart around a point of my divisor, the holomorphic sections grow depending on the weights. So H alpha, let me just roughly say it looks like this. Where I should have 2s here. Okay, so I already said in general, it depends on the nilpotent part of the Levy projection of the residue. And that causes real problems if you want to try to have a gauge theoretic construction of this moduli space where you're not in full flags. If you allow the Higgs field to have this nilpotent part of the Levy projection of the residue be non-zero, then your kind of background metric you choose needs to depend on that data. But, okay. Okay, good. So that's a non-abelian Hodge works like this. And from such a metric, we'll play the same game. I have d bar E plus the adjoint of phi. I have DEH plus phi. And this, from this object, there is a natural weighted flag structure at the points of the divisor. And this is what Carlos talked about in his talk. And that weighted flag structure comes from, the growth of holomorphic sections with respect to this holomorphic structure at those punctures. Okay, and it's not just the same as this alpha. And so it changes, by, Carlos went through the computations during his talk. So let me just recall what those are. So here is going to be what I'll call the weight. And here is the eigenvalue. This is the Levy of the residue. Okay, this is that Levy projection in the full flags case. So for the Higgs bundle, this is what we're calling alpha. Okay, each weight has associated eigenvalue. Let me call that mu. That's a complex number. And now, how does that change when I go over here? Well, so for I get a new weight, beta, which is alpha minus twice the real part of mu. And I get a new eigenvalue of this, of the residue of this holomorphic connection at that point, and that's, I won't give it a name, but it's alpha plus 2I times the imaginary part of mu. Okay. I didn't do a very good job of respecting the bold lines. So what I want to do, right, is recall my two parameter family from before, which was d bar e plus lambda r by star r plus d e h plus lambda inverse hr r phi, and ask, well, what is the table for this family of connections? How does it depend on lambda and r? And again, I think Carlos talked about what the answer is. And I guess it was computed first by Mochizuki. But let me just call this star so I don't have to rewrite it. So here, this should really be thought of, I think, in this computation as twice the real part of the conjugate of mu bar, which is, of course, the same thing. But this is the eigenvalue of phi star. Okay, and so when I multiply by lambda r, that eigenvalue changes by lambda r. So here the answer is alpha minus twice the real part of lambda r mu bar. And again, as Carlos said, since lambda is complex, you can't pull it out. Okay, and this guy, you should think of the imaginary part as minus mu bar plus mu. And this is the contribution from phi star, and this is the contribution from phi. So what I get here is minus lambda r mu bar plus alpha plus lambda inverse r mu. Okay, and now remember the conformal limit. So this is somehow the holomorphic connection, not multiplied by lambda. When I multiply by lambda, this will stay the same, and that'll get a lambda. Yeah. Okay, and then remember the conformal limit is when I fix h bar to be lambda inverse, sorry, r lambda inverse. And when I do that, this term becomes r squared h bar. This term becomes h bar inverse. And so, star in terms of h bar is, let me just read it instead of rederiving it, alpha minus the real part r squared h bar mu bar. And then here we get minus h bar r squared mu bar plus alpha plus h bar inverse alpha. Okay, so the theorem, I'll end here. I'll just mention it. I think I've already hinted at it. Yeah. Yes, thanks. And mu bar. Fredrickson and Wentworth. Oh no, Richard, your name is, I have to do it like that so it makes on the board. Is the same thing as a compact case. And the proofs are really in the same theorem, especially this, slice coordinates. But the gauge theoretic setup is, well, more delicate and will confuse us for a while. But we think we do finally have all of those proofs, let me point out that the main kind of thing is that in the limit, as r goes to 0, what happens to this table? Well, this goes, well, if you do it like this, that goes to 0, and this goes to 0. Okay, so the weights stay the same. They're alpha the whole time. I mean, in the answer, in the limit. And the eigenvalue transforms in this very natural way as you just add h bar inverse times the eigenvalue of the Higgs field. Okay, so the table is the conformal limit table is alpha, meaning that's constant. And if I want to think of it now, I'll switch back, Carlos, to the eigenvalues of the h bar connection. It's h bar alpha plus mu. Okay, so in particular, you see that the conformal limit makes sense as defining sections of this space because in the limit, the weights are constant. Okay, so that's it. Thanks.
Thank you for the privilege. Thank you for the talk. Very nice. So the Beilinson-Drinfeld operas are related to the Borel, right?
Yeah.
And so is the Hitchin section.
Yeah.
But now, what about the conformal limit of other of the what Steve called the magical components that you yourself introduced a notion of pair that involves a different parabolic group.
Yeah.
Is it?
So
You work that out, or
yeah, I mean, somehow, let me just write down the equations real quick, and you'll see that it's like, so these, the kind of points of these global slice equations, there's a psi, which is upper triangular, and a beta, which is strictly upper triangular. These are like things you add to the Hodge bundle. They satisfy the equation that d bar psi plus phi 0 plus beta phi 0 plus psi is 0. Okay, that just means that it's a new Higgs bundle. That's the holomorphicity equation. And then they satisfy another equation, which is okay. So in the case where you consider these Sladovy slices, those are very special Hodge bundles coming from SL2s, like the uniformizing SL2, which you then put into G by some choice of SL2. So you know that this kind of set of solutions is like as a Lagrangian, so it's half dimensional. And for those very special SL2s, you can compute the dimension of the set of solutions here where beta is equal to 0. So beta equals 0 means that's 0 and that's 0. And in the SL2 case, that's also half dimensional. So that describes all of them. And what are you doing? You're adding holomorphic things in highest weight spaces. That's what this, so this slice and the Sladovy slice, agree. And the answer for the conformal limit is you just apply non-abelian Hodge to the base point, and then you tack on psi to the holomorphic connection. So that is what the conformal limit is. It just matches up these two parameterizations. And that's somehow the simple case where in the stable manifold, there are no kind of extensions of the bundle to be added.
so the answer is yes. I mean, the conformal limit, you can identify the conformal limit of the magical components to the operas.
Yeah, the answer is yes.
Very
Sorry for that.
Just to make clear. Thank you.
Does the conformal limit respect Hecker transformations in any way? I mean, the reason I ask is that, the work with Tamas,
Mhm.
we related the Hitchens section to the other
To the
upward flows
other-
by Hecker transformations. Each of these upward flows has a limit. And so, I mean, it might be a special situation, but for example, you could have, I mean, the operas are basically where you have like a scalar nth order differential operator, which
Mhm.
relates to a GLN flat connection. But
Yeah.
you can have apparent singularities. In other words, the second or nth order operator looks like it has a singularity, but the corresponding holomorphic flat connection doesn't.
Yeah.
I'm just wondering whether that is possible. I mean,
Well, it's possible. I can say yes to that one, but
well, I mean,
I
the
don't
Higgs
know.
field has to initially leaves fixed some vector space. Now,
That's right.
at a point. Now, as you're going in your conformal limit,
Uh-huh.
what's happening? So, I mean, one is the bad part maybe scaling away and you still get something.
I don't know. Like the holomorphic connection also like preserves some flag determined by, well, the Hodge bundle it's associated to. So there are a lot of invariant subspaces that, but I guess all those subspaces kind of on the point of that on the Higgs bundle side is they are moved by the Higgs field. So except for the last one. So I guess I just don't know. Yeah. It's an interesting question, of course, though.
So if I understood the way you presented the conformal limit is as a flow for, so you take a Higgs bundle, associate the corresponding flat connection, and then flow that with a suitable rescaling of the.
Yeah.
So is there a way of thinking of this conformal limit as something happening on the twistor space or on the Hodge bundle rather than the model space of flat connection? So I wonder if it has a more geometric and natural interpretation if you think of the twistor space rather than.
Well, I mean, from its definition, I would say I don't see how to do it, but I guess the theorem that Richard and I proved in this setting is that yes, it does. I mean, it defines these sections of the twistor space. At least, so if you if you can do it over C, right? You get these sections, and it's somehow like if you look at the C star action, it takes all this nice thing and it collapses it all to a fixed point. And so it doesn't kind of identify this Lagrangian with this Lagrangian. And what the answer of the conformal limit is a kind of, is you're scaling down, but you kind of are stretching back at the appropriate rate where you identify these things. But if you go to infinity, everything gets collapsed to the C star fixed point on the conjugate Riemann surface. So it's not like you get a nice, I don't know, identification with something at infinity also. Kind of the collapsing happens at infinity. I don't know if that answers your question, but just from the definition of the limit, I don't know.
Yeah, so can you say something, or do you know anything about how continuous this is? When you had a map from, M0 across C into C cross M0 into M Hodge.
Point I didn't make, right? Yeah, I mean, it's just not continuous.
Are you sure that it's not continuous, or you just?
It must not be continuous, or else so if you took a wobbly fixed point, it would have a limit as you went to infinity. And the conformal limit is holomorphically identifies these this C flow down to the fixed point. So if it was continuous, I think you would get a P1 in the de Rham space. because, on the Higgs bundle side, you have this flow. If it's in the nilpotent cone, it'll complete up to a P1. And the conformal limit kind of matches that C all the, holomorphically with an affine line in the Durand space.
Okay.
Yeah, so that's the non-abelian Hodge is not holomorphic, and parts of conformal limit are, but it's not continuous. Okay, so.
What does he think? Holomorphic, but
Well, I mean, it's defined. There's natural stratifications, and they're holomorphic on each strata, but the closure structure of the strata on the Higgs bundle side, that's not a continuous. I forgot I'm being recorded.
Maybe can I ask one very small last orientation question? Do you know which, if any, of these three numbers the physicist would recognize as the gauge coupling constant?
No. I can know the answer to that question is. I know my answer to that question is no.
The similar question: why is H bar? Why do you use H bar?
Yeah, because Gaiotto used H bar when he made the conjecture,
Okay.
and that's where. And it's a good advertisement.
Okay. Well, if there's no further questions, then let's thank them. Again.